Hello everyone. Today we will be discussing the second topic, which is about rotating balancing. So we will discuss both static and dynamic balancing. Now, to give you a brief idea about the content of this module, so I will be covering these two topics. So the first one, which we already did in the semester one, was about torque diagram and speed fluctuation. And now in the next 2 weeks, so this week and the next week, we will discuss this new topic, which is about rotating balancing. So in addition to this, you will also need to work on the tutorial 5, and then you will need to submit tutorial 5, which is a requirement to be eligible for the class test. And the class test, which will be in the week 4 of this semester, consists of a 1 hour class test. And the class test will be only in these two topics, that is the torque diagram and speed fluctuation, and rotating balancing. And this test will be in the tutorial slot. It will be online test, and this will contribute 15% to your module marks. Okay, so to come to the today topic, so as I explained earlier, that today we will be discussing about the rotating balancing, both static and dynamic balancing, and so we will divide the whole lecture into three parts. So first we will discuss a case where we will have a single out of balance mass, as you can see in this figure, that if you have this chopped and then there is an out of balance mass. We will discuss this in a minute. So how you will balance this system here. In addition to this, we will also then discuss the second topic, which is you may have several out of balance masses, but in a single transverse plane. As you can see in this figure, that you have multiple masses, M1, M2, M3, but all are uh, in a different directions, but all are in a single transverse plane. And finally, we will discuss the most complicated case, which is the out of balance masses in a different transverse planes, uh, and displaced along a shaft. And at the end, we will discuss some numerical example uh, to give you an idea of how to apply the theory to some practical problems. Okay, so to just start with the static balancing. So as we know that the if a system is statically balanced, so it will stay in any angular position without rotation. So if you consider this simple experiment here, which is the knife edge experiment for static balancing, you have a shaft here, a circular shaft, and a disc is attached to this circular shaft, a circular disc. And if there will be an out of balance mass in the disc, so as you can see here, that this out of balance mass is represented by a point mass m in this figure here. So this is the front view, and this is the side view of this same experiment. So if we have this out of balance mass in the disk, so if we rotate this shaft, it will always come back to this position. So this means that the shaft is not balanced. If the shaft is balanced, so then we will be able to satisfy this condition, that the system will stay in any angular position without rotation. Okay, so the process of balancing of an object against a static force is what we call static balancing. And static force is mainly the gravitational force. So if you consider this two mass system here, which you can see in this figure here. So if you have a shaft again here, and there are two masses attached to the shaft, this is M1, this is M2. So in this case, as you can see, that the both these shop out of balance masses are horizontals, and the weight of this mass is W1. The weight of this mass is W2 here, and as you can see, the center of gravity of this mass is this point here, and the distance of the center of gravity from the center of this uh, shop is R1. Similarly, in this case, what do you have is that the center of gravity is this point here, and the distance of the center of gravity from the center of the shop is R2 here. So in this case, the weight is obviously in the vertical direction. So W1 is the weight of this mass, and W2 is the weight of this mass here. Now, if you want to calculate the moment of the mass 1, which is this one here, so the moment will be equal to the weight times the perpendicular distance, so which is R1 in this case here. And for this mass, the force is W2, which is the weight, and the perpendicular distance is R2 here. So the moment of the mass 2 is W2 R2. Okay, and as we know that the W1 will rotate the shaft, will try to rotate the shaft in clockwise direction, or in this direction here, and the W2 will try to rotate the shaft in this direction here, so in the counterclockwise direction. So now we know that the condition of static balancing is that the clockwise and counterclockwise moments must balance. So if the clockwise this clockwise moment, if it is equal to the counterclockwise moment, so then the system will be statically balanced, and then it can stay at any angular position without rotation. So then we can write the condition of static balancing is that W1 R1 should be equal to W2 R2. Okay, now we can consider a bit more complicated case here. So in this case, we have again a shaft, and now three masses are attached to the same shaft. So we can say that this is our three mass system here, and this is again the isometric view, and we are also given the side view of this figure here. Um, Again, we can see that for W1, which is the weight of mass 1, W2 is the weight of mass 2, and similarly W3 is the weight of mass 3, and point 1, 2, and 3 are the center of gravities of these masses. Now in this two mass system, the masses were horizontal. So the R1 and R2 were the perpendicular distances between the center of gravity and the center of the shaft. But in this case, the masses are at some angle, as you can see from this side view. So here in the side view, what we can see that we have this W1, and then this R1 is the distance of the center of gravity from the center of the shaft. Similarly, R2 is the distance of the center of gravity of mass 2 from the center of the shaft, and similarly for the mass 3, we have R3 here. And obviously these R1, R2, and R3 are not horizontal. So therefore, we also need the angles of these lines with the horizontal. So the alpha 1 is the angle of R1 with horizontal. Alpha 2 is the angle of R2 with the horizontal, and similarly alpha 3 is the angle of the R3 with the horizontal. Now similar to the two mass system, this system will be statically balanced when we can satisfy the condition that the clockwise and counterclockwise moments must be the same. So as we can see from this figure here, that the W1 will try to rotate this system in the counterclockwise direction, and W2 and W3 are trying to rotate the system into the clockwise direction. So this is the clockwise direction here. So if we want to write the condition of static balancing for this three mass system, so how this we can write is that the counterclockwise moment should be equal to the clockwise moment. So in this case, the W1 is trying to rotate the system in the counterclockwise direction. So uh, the moment of W1 is W1, which is the force, and the perpendicular distance between the center of the shaft and the W1, which is R1 cos alpha 1. And on the right hand side, what we have is that the W2 and W3 is rotating the shaft in the clockwise direction, or trying to rotate the shaft in the clockwise direction. So the moment of W2 is again W2 R2 cos alpha 2, and similarly for W3 it will be W3 R3 cos alpha 3. So this is the condition of static balancing in this specific case. So if the right hand side is equal to the left hand side, or the clockwise moment is equal to the counterclockwise moment, so then the system will be in static balancing. Okay, now to discuss the dynamic balancing, first we need to understand the centripetal and centrifugal forces, and then we will be able to understand the dynamic balancing. So if you consider this figure here, in this figure, the mass m is rotating uh, at angular velocity omega about a fixed point or a support at O. So this is the mass which is rotating about this point here, and the distance of the mass from the O is r here. Okay, so the center seeking acceleration in this case is that is what we call is centripetal acceleration, can be written as omega square r. So omega square r is the centripetal acceleration of the mass here, and the magnitude of this centripetal acceleration is omega square r. Now, what will happen if we try to separate this mass from this point here? So that is what we want to, if we want to draw, for example, uh, the free body diagram of the mass here. So we know that the mass here is so we will need to apply the force that we will need to apply on the mass here. So that is how we will draw the free body diagram. So in this case, you can see that m omega square r. So if you multiply mass with the angular mass with the centripetal acceleration, so you will get the centripetal force here. So this is what we call is the centripetal force. And in addition to this, the mass will exert the same force on the support here, and the magnitude of this force is again m omega square r. And again, this is what we call is the centrifugal force. So if we separate these two points, that is, we want to draw the free body diagram, and the mass m is require a centripetal force of magnitude m omega square r, and therefore an equal and opposite centrifugal force is exerted on the support at O. Okay, so now this centripetal force, which is m omega square r, as you can see in this figure here, can be very large, even for a small mr values. And the reason is because this equation depend on three parameters, m, r, and omega square. So this means that if even if mr are small, but if the shop is rotating at a very high rpm, so this means that the angular velocity will be very high. And in this equation we have omega square. So that is the note that the importance of this omega square for a very high speed machinery. So if the omega is high, so the centripetal force and obviously the centrifugal force will be very, very high. And now the problem associated with this out of balance force, because this can cause excessive bearing loads. So obviously if there is this out of balance some mass in the system. So for example, if we have a shaft and some gear is attached to the shaft, and if there is an unbalanced mass in a gear, so and if the shaft is rotating at a very high rpm, so there will be excessive bearing loads on the bearings, which can ultimately cause failure in the bearings. And in addition to this, it will create machine and structural vibration, and it can also create component failure through metal fatigue, and it will also create and transmit noise. Uh, so noise and or vibration can lead to excessive operator fatigue and injury. So that's the reason that we want to balance this unbalanced system. And vibration of the handheld power tools may cause temporary or permanent damage to the blood vessels, nerves, and muscles. And in medical terminology, there is a specific name for this. So this is what we call is a collective injury, that is called is hand-arm vibration syndrome, HAVS. And there is also other name associated with these, which is you can say is a dead hand and dead finger or white fingers. And this NVH, which is noise, vibration, and harshness, is obviously of major importance in automotive and aerospace industry. Okay, so the dynamic balancing can now we explain that it's a process of balancing of an object for dynamic forces. So when the system is rotating at some rpm, so there are some centrifugal forces associated with it. So the process of balancing of an object for dynamic forces, which is centrifugal forces. So when dynamically balanced, there should be no turning or twisting moment along the axis of rotation. So which you can see in a minute. So when the shaft rotate, as you can see in this case here. So if there are some unbalanced masses attached to a shaft, so in this case, as you can see, there is this W1 and this is the mass M2. So two forces acts on the assembly that must be balanced. So one is the centrifugal forces around the shaft. So as you can see in this figure here, that if this shaft is rotating with some angular velocity here, so we will be having one centrifugal force which is in this direction, and one centrifugal force will be in this direction here. There will be two centrifugal forces, so we can say that FC1 and FC2. But in addition to these centrifugal forces, as you can see that these centrifugal forces will also create this couple here, because one force is here and one force is here. So this can create this twisting moment, which is along the axis of the shaft here. So if the shop rotate, so two forces act on the assembly that must be balanced. So we should in the dynamic balancing uh, we will make sure that we have balanced the centrifugal forces which is around the shafts, which is the FC1 and FC2. And in addition to this, we should also balance this moment or couple which is trying to twist the shaft along its length or longitudinal axis. Now, as you can see in this case here, that we have a two mass system here. So this is this is the mass 1 and this is mass 2. So we can see that this two mass system may be statically balanced, as we explained in the static balancing case, that the system was statically balanced but not dynamically balanced, and due to the possible this twisting moment. So although the MR1 should be equal to maybe MR2, so this MR1 may be equal to MR2, or maybe W1 will be equal, W1R1 may be equal to W2R2. So this mean that this system may be this is statically balanced. But because there's a distance between the two forces, and this can create a couple, which is, as you can see in this case here. So this means that the we we also need to to balance against this moment here. So if a system is dynamically balanced, so we should balance the forces, and we should also balance this twisting moment here. So if out of balance mass exists in more than one transverse plane, then in general static balance will not ensure dynamic balance here. So now we can now consider these three possible cases, which we will discuss step by step. So the first one is a single out of balance mass, as you can see in this figure here. The second one is we can have several out of balance masses in a single transverse plane. And the final case is if we have the out of balance masses in a different transverse planes and displaced along the shaft. Okay, so uh, the first and the most simple case is that if you have a single out of balance mass in a system. So if you consider this shaft and there may be some pulley or gear or some other component attached to it, and there may be some unbalanced mass in the system, and the mass here is represented by M1. So M1 is the out of balance mass, and R1 is the distance of this M1 from the center of the shaft, and the shaft is rotating at some angular velocity here, which is omega, and the shaft is supported at two ends. So this is bearing 1 and bearing 2 here. Okay, so as we can see that because the shaft is rotating at some angular velocity here, so there will be a centrifugal force m1 omega square r1, which this mass will exert on the shaft, and this out of balance force on the shaft will transmit it to the bearings, and the out of balance may be represented by a vector of magnitude m1 omega square r1 and rotating with the shaft at omega. Now obviously the shaft is rotating, so this means that the out of balance mass will also be rotating with the shaft, and this means that the centrifugal force will also be rotating with the mass here. So now because this will create a load on the bearings, so our aim here is to balance this system so that there is no load on the bearings. Okay, so now we want to balance this system here. So the rotating balance is achieved by placing a single balancing mass M1 diametrically opposite to M1, and such that, so as you can see in this figure here, that you have M1 and R1, so which was the original uh, out of balance mass, and the distance was this, and then this is the centrifugal force M1 omega square R1. So now we we want to balance this system here. So we are attaching here another mass to this system, which is just directly below this mass here, and the mass here is a capital M1. So this is the balancing mass, and the distance of this mass is R1 from the center of the shaft. So a capital R1. Now this system will be in balancing when F we can satisfy this condition that that F the this force, which is M1 omega square R1, is equal to this force here. So M1 omega square R1. So if we can satisfy this condition here, that if the centrifugal force of the original out of balance mass is equal to the centrifugal force of the balancing mass, which is M1. So if we can satisfy this condition, so then the system will be in balancing here. And now, as you can see in this case here, that we have omega on this side and omega square on this side. So this means that we can even cancel this omega here. So therefore we will have M1 R1, which is equal to M1 R1. So then this means that omega is even not important here. So this means that the only important thing here is the mass time the radius. So because the condition was M1 R1 equal to M1 R1, so this means that the mass times radius product is the important quantity when considering rotating balancing. And if the system is in balance at one speed omega, so it is automatically in balance at every speed. So therefore we even don't have omega in the equation. Okay, so now if we just consider the system here, so if you consider the same system, that if you have, for example, uh, we have this M1, which was the out of balance mass, and this capital M was the balancing mass here. R1 was the distance of the balancing mass, and R1 small r1 was the distance of the distance of the out of balance mass here. And now assume that this is the position of these two masses here. So now if, for example, if you want to talk about the static balancing now, so if this system is statically balanced, so as we explained earlier, that it will stay in any angular position without rotation. And we know that the if we try to take a moment about O, so then we can say that due to gravity we will have two moments here. So then one moment is this capital M1 will try to rotate the system in the counterclockwise direction, and the small m1 will rotate it in the clockwise direction here. So if we take moments about point O, and let's take the the clockwise is positive, so what we will have is that m1g, and m1g is obviously, now we are talking about the static balancing. So these are the gravitational forces. So m1g, which is the weight, and the distance here is the r1 into cos theta 1. And similarly for this mass here, what we can have is m1g r1, and because this angle is theta 1, so this angle is automatically theta 1. These are vertical angles. Okay, so we have this condition, this equation here. So if the system is dynamically balanced, so we shown previously that m1 r1 was equal to m1 r1. So this was the condition of the for this one mass system, the dynamic balancing condition. Um, so if we already showed that this m1 r1 was equal to m1 r1. So if you look at this equation here, and if you put m1 equal to if you put this m1 r1 equal to m1 r1, then this means that this equation should be equal to 0, and there will be and the net moment will be equal to 0. So this means that the clockwise is equal to the counterclockwise. So this simply means that therefore the moments about O is 0, and that is if the system is in dynamic balance. So then it will also be in static balancing. So this is very important point here, that if a system is in dynamic balance, so it is automatically balanced in static. But you cannot assume that if a system is in static balancing, that it will be in dynamic balancing. So this is very important point. So you should remember these points always. That the if a system is dynamically balanced, it is balanced statically automatically. But if a system is statically balanced, so you cannot assume that it will be balanced dynamically. Okay, so now we can go to our second case here. And the second case is that we have these several out of balance masses in a single transverse plane here. So as you can see that you have again this shaft here, and along the shaft at some specific position here, we have three out of balance masses here. So one is m1, one is m2, one is m3, and the position of each mass is also given. So the position of this mass is r1, this mass is r2, this mass is r3. And if you consider this arbitrary reference line here, so you are also given the angles of each this line, so r1, r2, and r3. Okay, so now we want to balance this three mass system here, and obviously the system is also rotating at some angular velocity here. So the out of balance force m1 omega square r1 etc. may be represented by vector of correct or relative magnitude and angular positions here. And this is also a very important point, that you only need mass times radius. So you need only the mr value. You don't need omega because the product, since this omega square is constant for all the vectors. So the magnitude and position of the balancing mass may be found out graphically or analytically. So this balancing mass, which is capital M, which you can say is, if you add to this system, the system will be statically balanced and dynamically balanced. So if you add this mass, so how you will calculate this mass and how you will find its position. So you can do this using two procedures. You can do this graphically, or you can do this analytically or mathematically. So first, let try to explain the graphical procedure. So the graphical procedure is is that you will try to calculate, find out the centrifugal forces or product of the mass and radius of rotation exerted by each mass on the rotating shaft. And then you will draw the vector diagram with the obtained centrifugal forces, such that M1 R1 represent the centrifugal force exerted by the mass M1 in magnitude at some suitable scale and direction theta 1. And similarly, then you can draw M2 R2 and M3 R3 at angles theta 2 and theta 3 to represent the centrifugal forces of other masses, which is M2 and M3. And finally, the closing side represent the resultant forces in magnitude and direction. And the balancing force is then equal to the resultant force, but in opposite direction. So it's just a simple vector addition here. So the Fc, which is the centrifugal force, is just equal to mr, and m is the balancing mass here, and r is the radius of rotation. So now we will try to do this with some uh, like the using the graphical procedure here. So for example, if you have these three masses here, so m1, m2 and m3 here. So obviously the centrifugal force of mass m is in this direction here. So this is the centrifugal force of this m1. So you can call this f1. Centrifugal force of this m2 will be in this direction, which is f2, and centrifugal force of this uh, 3 mass will be in this direction here. So you have here three forces, and obviously we know that the centrifugal force, so F1 is equal to m1 r1 omega square, F2 is equal to m2 r2 omega square, and F3 is equal to m3 r3 omega square. Now in this case, because omega square is with each force here, so we can just ignore omega square because it will just increase the size of the vectors. Otherwise, it's adding no information to the plot here. So again, if we want to so it is just a vector addition that you want to calculate the resultant of these three vectors, f1, f2 and f3. So obviously the way you will do it, that you will just draw this reference plane. So this is our reference plane here. Okay, so we can for example start from this point here. So you will draw f1. F1 in this case is m1 r1. So you know the angle theta 1, which is this angle here, and you know the direction, which is this direction here, and the magnitude is m1 r1. So for example, if this is this is m1 r1, and the angle here is theta 1 here, and then you will the second force that you can draw is this f2 here, and the angle that f2 is making with the horizontal is theta 2. So if we again draw the horizontal here, so this will be our m2 r2, and the angle here is theta 2 here. And finally we have F3. So again, if we draw the horizontal line here, so the F3 is in this direction here, and the magnitude is going to be M3R3. And finally, the resultant that you can draw in this case will be from here to here. So this is our resultant. But as we say earlier, that that you should draw a force which is the balancing uh, force should be opposite to the resultant. So the mr is equal to the resultant but in the opposite direction. So this is our mr value, so which is the required closing vector for the balancing. So as you can see in this case, so if you add this mr to the system, what will happen that it will just close the polygon, and the resultant will be equal to 0. So the system may be balanced by adding material to provide the closing vector mr at angle theta. In other words, you can remove material at angle theta minus 180. So this is how you will add this close this whole system here. You can also solve this system using analytical procedure. So analytical procedure is again very straightforward, as you will do in vector addition. So how you will do this? You will again find out all the centrifugal forces. You will resolve the centrifugal forces in horizontal and vertical direction, and then you will find out their sum, that is the summation of all the forces which is in horizontal direction and vertical direction. So it will be summation of all the forces in horizontal will be equal to m1 r1 cos theta 1, and similarly m2 r2 cos theta 2, and plus so on, depending upon the number of forces. And then you will do the same for the vertical case, m1 r1, and then it will be, for example, sine theta 1, m2 r2 sine theta 2, and so on. And then you will try to calculate the magnitude of the resultant centrifugal force. So which you can do this by using the Pythagoras theorem, that summation of all the horizontal square and obviously the vertical sum square. And then you also, because it's a vector, so you also need to calculate the angle. So the tangent theta will be equal to the summation of the vertical and obviously summation of the horizontal forces. And then the balancing force is then equal to the resultant force but in opposite direction. So the fc is obviously the mr. So m is again the balancing mass and r is the radius of rotation here.